Hi folks, and welcome back to Physics with Captain Rod. I'm making this video here to talk about a concept called flux. And we're going to talk about two kinds of flux. We're going to talk about electric flux created by areas in the electric fields, and we're going to talk about magnetic flux. So we're going to start with this example here on the left. So imagine we've got this uniform electric field as illustrated here by these green lines. Now these are supposed to be electric field lines. Remember that the electric field vectors are tangent to the field lines at any given point. So if I picked a spot like right here, the electric field vector would point to the right. Pick any other spot on the page here, the electric field vectors point to the right. Equal spacing means uniform field. And what you'll notice here, we've got this hula hoop here. And imagine like this is the side coming at you, this is the side going away. Now, on the hula hoop, I'm going to draw a very important vector here. I'm going to draw a vector that's got direction only that makes a right angle to this surface area here, and that's what I'm going to call this normal vector. That'll come up later in the discussion. Now, I guess while I'm at it, let me draw normals on this one and this one. And again, these are unit normals. Their direction is all they have, and they're at a right angle to the surface area here. Now, flux in general is field strength times area. I'll put just Fs times A for now. So in this example, the electric flux through here is going to be the magnitude of the electric field times the area of this circle, which is pi r squared. Now, there's a little qualifier here. Only electric field components that go through the normal, or that are in the direction of the normal, create flux. Any field components that make a right angle to this normal and are therefore parallel to the surface don't create any flux through the surface. So in this example, the electric field and the normal, they're in the same direction. Basically what that means is all of this electric field vector is going through the area. No sines and cosines required. So if we just put in numerical values here, and I just made up numbers off the top of my head, that's going to be 100 Newton per Coulomb times pi times the radius of this thing squared, and I wrote that down somewhere. I'm going to use R equals, what I use, 0.5 meters. This is just a completely made up example. So it's going to be, let's see, field strength times area times 0.5 meters, and that's squared. If we go through and calculate a value here, I've already done this, I get 78.5. And units, you can always take them at face value. It's Newton per Coulomb times meter squared. So Newton meter squared per Coulomb. So this number represents what's called the electric flux through the surface. All right, now we're going to calculate the electric flux through surface 2. Now I'm going to go ahead and draw an electric field vector right at this spot. Same length as this one. There's our 100 Newton per Coulomb. And in this example, we're going to imagine a 60-degree angle between the electric field and this normal. Now, if you kind of picture this vector like in terms of components, it's got a component in the direction of the normal. It looks like this, and a component at a right angle to the normal, which looks something like this. Notice that all of this vector goes through the area and none of this one does. This is the vector component when we calculate the electric flux through this surface. This is the component of the electric field that's, well, I could either say parallel to the normal, or we could say is perpendicular to the surface area. Either one gets that done. Now you'll notice, if I think about this vector in terms of components, 100 cosine 60 is the component here that makes a right angle to the surface area. So that second flux is going to look like this. 100 Newton per Coulomb times cosine 60 gives the component of this vector that goes through this area. And then times, again, the surface area here, pi r squared. That's going to be pi times 0.5 meters squared. And we get, let's see, I did this somewhere. Well, I guess I'm just going to redo it here, if you just give me a moment. 39.3 is close enough. 39.3 Newton meter squared per coulomb. Whoop. Pardon me. Okay, next let's take a look at this animal right here. So when we calculate that third flux, you'll notice now that the normal here is making a right angle to the field line. In fact, if I draw in an electric field vector right at this spot, there's my 100 Newton per coulomb. You notice that none of this goes through the cross-sectional area. And you'll notice that the angle between the 100 and the normal is 90 degrees. If I were to actually calculate a flux numerically, it's 100 Newton per coulomb times the cosine of 90 degrees. That would give the component that's in the direction of the normal times the area, pi times 0.5 meters squared, and we get 0 out of that. So let's see. Important thing about this video. One, how is flux calculated? Right. In general, it's field strength times area, but the field strength needs to be the component that's parallel to the normal vector. I'll just say parallel to n hat. If I wanted to write a little formula for it, let's see, how about, I'm going to put v for vector because it can be any different type of vector. And I'm going to put a magnitude on it, times the area times the cosine of the angle between whatever this vector is and, whoops, get rid of that, and the normal. You can calculate a flux for electric field vectors, for magnetic field vectors, for gravitational field vectors. And since this video is getting to be a little longer than I want, I think I'll just leave it right there. I was going to do some magnetic field examples, but I think I'll save those for another video. So this is how we calculate flux in general, field strength times area. And another important thing to notice is when a flux is maximum and when it's 0. So flux is always a maximum when the area makes a right angle to the field that you're dealing with. And it always is 0 when the area is parallel, if you will, to the field that you're dealing with, right? That's probably good enough for now. Hope that this video gives you some understanding of what flux is. Have a great day.